Welcome to Chemical Process Safety. This video will answer the third question of pressure relief design, which is how to size it. The sizing of pressure reliefs is going to depend on the phase of flow and the type of relief, which we discussed in the last video. One of the key design parameters is the overpressure, and that is defined as the pressure inside the vessel during the relief minus the set pressure. The set pressure is, again, the designed pressure at which the relief device is set to open, and that would be manufacturer specified. So just as an example, if the rupture disc is set to rupture at 100 psi, but the pressure inside of a reactor during the relief is 150 psi, 150 minus 100 would be 50 psi would be the overpressure in that situation. So to make a long story very short, we're going to talk only about liquid flow, but whether you're talking about liquid or vapor flow, the theory is very similar to that of a source model because what we have is material flowing through an orifice. So let's start with liquid flow through a rupture disc, which is, again, the simplest situation. That is literally just flow through a hole. So we've got our equations that the volumetric flow rate is equal to the area times the velocity, again, just by units. And because we're interested in finding what the area is, we can rearrange this equation to obtain the volumetric flow rate divided by the velocity. And then, again, just as we did back in the source model module, I can find the velocity of the liquid flowing through the orifice by performing a mechanical energy balance. So the integral term can be simplified down to just simply delta P over rho because we have an incompressible fluid for a liquid. The height change is going to be negligible and there's no shaft work. Rearrange and follow the same exact logic. So for the sake of concision, I'm not going to go through the entire derivation again. It is the exact same. So you find that the velocity is the discharge coefficient times the square root of 2gc times delta P over rho. Again, just to remind you what GC is, because that's an oftentimes forgotten about parameter. That is the unit conversion, I like to think of it. So for SI units, GC is 1, and for US customary units, it is equal to, it has the same numerical value as the acceleration due to gravity. I can then plug this into this equation to find the area and obtain this expression for the area. So delta P is going to be the pressure difference across the valve. Because there's oftentimes funniness involving the units. So in the United States, for example, you're not going to find rupture discs in terms of centimeters or meters. You're going to find them in terms of inches. So the textbook has this very handy and helpful fixed unit expression that uses all US customary units. And you can derive this for yourself. It's a little bit, it's not a ton of work, but I've done it once and it's more cumbersome than I had the taste for. But anyway, you end up getting this 1 over 38 factor, and that basically accounts for all the unit conversions that you would need to do in order to have this be a dimensionally consistent equation. So you are, the downside of using this equation is that your units have to be specified as such. So for example, if your flow rate was gallons per second, you would have to convert that flow rate into gallons per minute in order to use this 1 over 38. There is no wiggle room, no flexibility that you can use in defining your units. Situation 2 is the conventional spring-operated relief valve. As a first approximation, you can model it as flow through an orifice. But the downside here is that this equation does not account for viscosity or varying area due to spring compression. So if you think about it, if I just imagine something with a spring, I can either compress that spring all the way, and there I would have potentially more area. So the area is the cross-sectional area. But you can imagine, depending on how open or closed that gasket is, you could have more relief area due to the spring compression. So there's all these correction factors that get introduced as a result of this. So C0 is the same as it has been, but we've got these three parameters, KV, KP, and KB. in addition to the set pressure and the back pressure there. So the book has graphs that tell you what the values for each one of these corrections are. Just in general, these parameters are going to be less than 1 or around 1. Starting with KV, the viscosity correction. This is going to account for additional frictional losses for high viscosity flows. So the logic is if you have higher viscosity, you have lower Reynolds number, lower KV, and a higher relief area is needed. So if the flow is moving kind of slower is how I like to think of it. Because of the viscosity, you need a greater relief area. So all you do is you go to figure 10.2 in the textbook and you obtain the value of KV based on the Reynolds number. Now, the challenge here is that the Reynolds number itself is going to be a value of a function of the velocity. However, remember what we're trying to find in the first place is going to be the velocity itself. So you have to iterate. In other words, choose a Reynolds number, calculate the correction factor, work out the whole problem, and then kind of guess and check. If you don't want to guess and check, in the footnotes of this table, there is an empirical relation that you can use instead. If you plot this out, it is going to be the same shape of this curve. And the benefit to having an analytical expression is that you can then use GoalSeek or some other equation solver using Python, for example, or whatever you want. So that is the viscosity correction. The second correction factor is the overpressure correction, KP. This accounts for discharge pressures being over the set pressure, or the degree of openness of the valve. In the updated expression, this was delta P before, so just show you that. It was delta P in the rupture disc version. It's been replaced, and that's accounting for this factor. The base assumption is that the pressure inside the vessel is 1.25 times the set pressure. And if it's not, then KP is going to correct for this. So you'll notice for a 25% overpressure, we're at about 1. The lower the overpressure is, the lower KP is, and the larger relief area that you need. So again, you can obtain it from this graph, and this graph also has equations for it. It's a piecewise function though. So depending on what the overpressure range is, we're going to have a different form of this equation. Finally, the back pressure correction used is only for balanced bellows. This compensates for the absence of back pressure. So using figure 10.4 here. If you have the conventional spring loaded, you would just say KB is equal to 1. Yeah, that's pretty much all that you need to know in terms of the parameters. So you look up each one of those 3 corrections and you plug it into this equation, and the rest of this is plug and chug. Now, the other important thing to mention is that when you perform these calculations, you're very likely to get an answer that is not a standard size. So like 9.72 inches, just for example. A manufacturer is not going to sell a relief valve that is 9.72 inches. So what you should do is always choose the next largest size. So you want to, it's almost like blackjack. Get as close as you can without exceeding what the area is. So always pick the next one up. And then finally, I have notes prepared, and the book goes into vapor flow through a rupture disc, but I don't like to cover that. It does get fairly complicated and fairly involved. If you're interested, I would highly encourage you to check out the book and to read about it. But for the purposes of this class, we'll stick to just liquid flow through a relief valve. Also, in addition to vapor flow, there's also a separate section for two-phase flow, so vapor and liquid, and that's even more complicated still. And also keep in mind that anytime you actually do have a rupture, it is likely going to be in the vapor phase. Probably not going to be in the liquid phase. So unfortunately, what we're covering is probably the least applicable. But again, have a look at the textbook section if you're interested. That will conclude this video. I will see you next time.